All right, so let's use the Sylow theorems and whatever else we can think of to talk about normal subgroups of groups of small order. So let's start by looking at groups of order up to 11. Now, what can we say? So group of order 1, trivial. Group of order 2, cyclic. Group of order 3, groups of prime order are cyclic. Group of order 4. Now, as we've noticed before, if you have a group of prime power order, then it always has a non-trivial center, right? If order of G is p to the n, then the center of G is non-trivial, and so you always have a normal subgroup of a non-trivial normal subgroup, in fact, central. And of course, if the order of G is p squared, you're actually abelian. So in any case, we know plenty about order 4. There is normal subgroups, it's abelian, blah, blah, blah. 5 is prime, they're cyclic. Order 6. Now, for order 6, let's see what the Sylow theorems say. We can look at the number of 2 Sylow subgroups and the number of 3 Sylow subgroups. The number of 2 Sylow subgroups is going to be congruent to 1 mod 2, and it's going to be going to divide the index of any of the 2 Sylow subgroups, which are order 2, so therefore the index is 3. So that tells us that N2 could be 1, but it could be 3 also. It just has to be odd and a divisor of 3. It could be 1 or 3. So maybe that doesn't have to be normal, but let's look at N3. This is congruent to 1 mod 3, and the number of them has to divide 2. And oh, what does that say? We're done. That means N3, it has to divide 2, and 1 more than a multiple of 3. It can only be 1. That's the only possibility. And so for order 6, we know that the 3 Sylow subgroup is normal. Okay. 7 is prime. 8 is a power of p. We can use that trick. 9 is a power of a prime. 10, let's look at 10. Again, now let's look at the Sylow 5 subgroup. So just kind of seeing the pattern, 2 didn't help us last time, let's just try the 5. This is congruent to 1 mod 5, 1 more than a multiple of 5, and N5 divides into the index, which is now 2, and you see just like before, that forces it to be 1, right? I mean, we can see what this pattern is actually, and maybe let's just write this pattern down. So if the order of G is, I don't know, p times m, then I can look at the number of p Sylow subgroups, and it has to be 1 more than a multiple of p, and it also has to divide m. But if p happens to be bigger than m, then that's going to force np to be 1, right? Because if it's 1 more than a multiple of p, it's either going to be 1 or p plus 1 or 2p plus 1. All those numbers would be bigger than m if p is bigger than m, right? So if G has order pm where p is bigger than m, then that tells us that np has to actually be 1. Okay, so that's the pattern, if we abstract it, that we just did for 6 and 10 with the 3 Sylow and the 5 Sylow. And of course 11 is prime, and so we're done with that. Which brings us to 12, and we'll do 12 next then.